Quantum mechanics isn't just a theory for physicists. It's the foundation of everything we see and experience. Prepare to have your understanding of the universe challenged as we delve into the fascinating world of quantum physics and its profound impact on the cosmos. You're holding a coin in your hand. In our everyday world, you know exactly where it is and how fast it's moving. But what if I told you that at the smallest scales of reality, particles don't follow these simple rules? What if that coin could be spinning clockwise and counterclockwise simultaneously, or could tunnel through solid barriers like a ghost passing through walls? Welcome to the quantum realm, a hidden layer of reality that operates by rules so strange they challenge everything we thought we knew about the universe. Today we're diving deep into quantum physics, exploring how the bizarre behavior of the tiniest particles shapes the very fabric of existence and revolutionizes our understanding of reality itself. For centuries, scientists believed the universe operated like a giant clockwork machine. Isaac Newton's laws of motion painted a picture of predictable cause and effect, where knowing the position and velocity of every particle would theoretically allow us to calculate the entire future of the universe. This classical worldview seemed unshakable until the early 20th century, when physicists began peering into the atomic realm and discovered something extraordinary. The quantum world doesn't just bend the rules of classical physics, it completely rewrites them. At scales smaller than atoms, particles exist in multiple states simultaneously, teleport across impossible barriers, and remain mysteriously connected across vast distances. These aren't science fiction fantasies. They're experimentally verified phenomena that form the foundation of our modern understanding of reality. What makes the quantum realm so fundamentally different? Scale matters in ways we never imagined. Just as the rules governing the behavior of ocean waves don't apply to individual water molecules, the principles that govern our macroscopic world break down when we examine the building blocks of matter and energy. One of the most mind-bending discoveries in quantum physics emerged from studying light itself. For over 2 centuries, scientists debated whether light was a wave or a stream of particles. Thomas Young's famous double-slit experiment in 1801 seemed to settle the matter, demonstrating that light creates interference patterns characteristic of waves. But then came Max Planck's work on black body radiation in 1900, followed by Einstein's explanation of the photoelectric effect in. These discoveries revealed that light also behaves like discrete packets of energy called photons, particles with no mass, but carrying momentum and energy. The shocking truth: light is both a wave and a particle, depending on how we observe. This isn't simply a limitation of our measurement tools, it's a fundamental property of reality. When we design experiments to detect light's wave nature, it behaves like a wave. When we design experiments to detect its particle nature, it behaves like discrete photons. Consider the modern version of the double-slit experiment. When we fire single photons through 2 parallel slits toward a detector screen, something remarkable happens. Each photon appears to pass through both slits simultaneously, interfering with itself to create the characteristic wave pattern on the screen. But the moment we place detectors at the slits to determine which path each photon takes, the interference pattern vanishes, and the photons behave like classical particles. This wave-particle duality extends beyond light to all matter. Electrons, protons, and even entire atoms exhibit this strange dual nature. The larger the object, the smaller its wavelength becomes, which is why we don't notice the wave properties of everyday objects, like baseballs or buildings. But at the quantum scale, this duality is impossible to ignore. The implications are staggering. Reality at its most fundamental level doesn't consist of definite properties that exist independently of observation. Instead, quantum objects exist in superpositions, combinations of all possible states, until the act of measurement forces them to choose a specific outcome. Werner Heisenberg's uncertainty principle, formulated in 1927, represents perhaps the most philosophically profound discovery in quantum physics. It states that we cannot simultaneously know both the exact position and exact momentum of any quantum particle with perfect precision. This isn't due to limitations in our measuring instruments. It's a fundamental feature of nature itself. The mathematics is elegant in its simplicity. The uncertainty in position multiplied by the uncertainty in momentum must always be greater than or equal to a tiny but non-zero constant, Planck's constant, divided by f. This means that the more precisely we try to pin down where a particle is, the less we can know about where it's going, and vice versa. But Heisenberg's principle extends far beyond position and momentum. It applies to other pairs of properties called complementary variables. We cannot simultaneously measure the exact energy of a system and the exact time at which it has that energy. This energy-time uncertainty has profound consequences, allowing particles to briefly borrow energy from the quantum vacuum, creating virtual particles that pop into existence and vanish in the blink of an eye. These virtual particles aren't mathematical abstractions. They have measurable effects. The Casimir effect demonstrates this beautifully. When two metal plates are placed extremely close together in a vacuum, virtual photons with wavelength longer than the gap between the plates cannot exist in that space. This creates a pressure difference that actually pushes the plates together with a force that can be measured in the laboratory. The uncertainty principle also explains why atoms don't collapse. In classical physics, electrons orbiting atomic nuclei should spiral inward, radiating energy until they crash into the nucleus, but quantum mechanics forbids. If an electron were to fall into the nucleus, its position would become extremely well defined, which would require its momentum to become extremely uncertain. According to the uncertainty principle, this would give the electron enormous kinetic energy, preventing the collapse. Superposition might be quantum mechanics' most counterintuitive principle. In our everyday experience, objects have definite properties. A light switch is either on or off. A door is either open or closed. But in the quantum realm, particles can exist in combinations of multiple states simultaneously until they're observed or measured. Schrödinger's famous thought experiment illustrates this principle through the paradox of a cat that is simultaneously alive and dead. While this scenario was intended to highlight the absurdity of applying quantum rules to macroscopic objects, it perfectly captures the essence of superposition at the quantum scale. Real quantum systems routinely exist in superposition. An electron can spin clockwise and counterclockwise at the same time. A photon can be vertically and horizontally polarized simultaneously. These aren't approximations or mathematical conveniences. Superposition is the natural state of quantum systems. The power of superposition becomes evident in quantum computing. While classical computers process information using bits that are either 0 or 1, quantum computers use quantum bits or qubits that can be in superpositions of both 0 and 1 simultaneously. This allows a quantum computer with just 300 qubits to perform certain calculations on more possible states than there are atoms in the observable universe. Superposition also explains the structure of atoms and molecules. Electrons don't orbit atomic nuclei like planets around the sun. Instead, they exist in probability clouds, superpositions of all possible locations where they might be found. These electron orbitals have specific shapes and energy levels that determine how atoms bond to form molecules and how materials exhibit their unique property. In classical physics, objects need sufficient energy to overcome barriers. A ball thrown at a wall will bounce back unless it's moving fast enough to break through. But quantum particles can accomplish something that seems impossible. They can tunnel through barriers even when they lack the energy to go over them. Quantum tunneling arises from the wave nature of particles. When a quantum wave encounters a barrier, most of it reflects back, but a small portion can leak through to the other side. The probability of tunneling depends on the barrier's height and width. Thicker or higher barriers are less likely to be penetrated, but the possibility never reaches zero. This phenomenon occurs constantly in the atomic world. The nuclear fusion that powers your sun relies on quantum tunneling. The protons in stellar cores don't have enough energy to overcome their mutual electrical repulsion through classical means, yet they tunnel through this energy barrier, often enough to sustain nuclear reactions for billions of years. Tunneling also explains radioactive decay. Alpha particles trapped inside atomic nuclei can tunnel through the nuclear force that normally confines them, causing the nucleus to decay. The rate of this tunneling determines the half-life of radioactive elements. Some tunnel out quickly, others take billions of years. Modern technology exploits quantum tunneling in numerous ways. Scanning tunneling microscopes use the tunneling current between a sharp tip and a surface to create images of individual atoms. Flash memory in our smartphones stores information by trapping electrons in potential wells, using controlled tunneling to write and erase data. Quantum entanglement represents perhaps the most mysterious aspect of quantum mechanics. When particles become entangled, they form a single quantum system, where measuring one particle instantaneously affects its partner, regardless of the distance separating. Einstein famously dismissed this as spooky action at a distance, but experiments have repeatedly confirmed its reality. Creating entangled particles typically involves starting with a system in a well-defined quantum state, and then separating it into parts that remain quantum mechanically connected. For example, when certain crystals split a single photon into two lower energy photons, these daughter photons are born entangled. Their properties, such as polarization or spin, remain correlated even when separated by vast distance. The strangeness emerges when we try to measure these entangled properties. If we measure one photon and find it vertically polarized, we instantly know its partner will be horizontally polarized, even if it's on the other side of the galaxy. This correlation isn't due to the particles carrying predetermined information. Bell's theorem and subsequent experiments have ruled out such hidden variable theories. Instead, entangled particles genuinely lack definite individual properties until measured. They exist in a superposition of all possible correlated states. The act of measuring one particle forces both particles to instantaneously decide on complementary outcomes, maintaining their correlation while respecting the overall conservation law. This isn't communication in any conventional sense. No information travels between the particles. The phenomenon is better understood as the instantaneous collapse of a shared quantum state that transcends ordinary space and time. The entangled particles remain part of a single, non-local quantum system until their entanglement is broken by interaction with their environment. The quantum revolution reaches its ultimate expression in quantum field theory, which describes the fundamental forces and particles of nature. Rather than thinking of particles as tiny billiard balls moving through empty space, quantum field theory reveals that what we call particles are actually excitations in underlying quantum fields that permeate all of space-time. Every type of particle corresponds to its own quantum field. The electromagnetic field gives rise to photons. The electron field creates electrons and positrons, and the quark fields generate the building blocks of protons and neutrons. These fields are dynamic entities, constantly fluctuating even in seemingly empty space, creating virtual particles that briefly appear and disappear in accordance with the uncertainty principle. This perspective transforms our understanding of the vacuum itself. What we perceive as empty space actually seethes with quantum activity. Virtual particle pairs continuously pop into existence, exist for fleeting moments, and then annihilate each other. These quantum vacuum fluctuations are more than theoretical curiosities. They have measurable effects on atomic energy levels and contribute to fundamental forces. The Higgs field represents a special case among quantum fields. Unlike other fields that have zero value in their lowest energy state, the Higgs field has a non-zero value throughout all of space. This cosmic field gives mass to particles through their interactions with it. Particles that interact strongly with the Higgs field have large masses, while those that interact weakly or not at all remain massless. The measurement problem in quantum mechanics has sparked decades of debate about the role of consciousness in physical reality. The standard Copenhagen interpretation suggests that quantum systems exist in superposition until measured, at which point the wave function collapses into a definite state. But what exactly constitutes a measurement, and where does this collapse occur? Some interpretations, most notably those championed by physicists like Eugene Wigner and John von Neumann, propose that consciousness plays a fundamental role in collapsing quantum wave function. According to this view, quantum superpositions persist until observed by a conscious entity, making consciousness a basic feature of physical reality, rather than an emergent property of complex matter arrangement. However, modern understanding suggests that consciousness isn't necessary for quantum collapse. Any interaction between a quantum system and its environment that results in information transfer can cause decoherence, the apparent collapse of superposition state. This process occurs constantly as quantum systems interact with photons, air molecules, and other environmental factors, typically destroying quantum coherence long before conscious observation takes place. Nevertheless, the measurement problem remains unsolved. Various interpretations offer different perspectives. The many worlds interpretation suggests that all possible measurement outcomes occur simultaneously in parallel universes. The de Broglie bomb theory proposes that particles have definite positions and velocities, guided by quantum waves, and cubism treats quantum states as subjective degrees of belief rather than objective features of reality. While quantum mechanics is often associated with the microscopic world, its effects extend to the largest scales of the universe. Quantum fluctuations in the early universe, amplified by cosmic inflation, created the tiny density variations that eventually grew into galaxies, stars, and planets. The cosmic microwave background radiation bears the imprint of these primordial quantum fluctuations, providing a direct observational link between quantum mechanics and cosmology. Dark energy, the mysterious force accelerating the universe's expansion, might also have quantum origin. Some theories propose that dark energy arises from the quantum vacuum energy density, though reconciling theoretical predictions with observations remains one of physics' greatest challenges. Black holes provide another arena where quantum mechanics meets general relativity. Stephen Hawking's discovery that black holes emit thermal radiation due to quantum effects near their event horizons revolutionized our understanding of both gravity and thermodynamics. Hawking radiation suggests that black holes eventually evaporate, raising profound questions about information conservation and the nature of space-time itself. The holographic principle, inspired by black hole thermodynamics, proposes that all the information contained in a volume of space can be encoded on its boundary. This radical idea suggests that our three-dimensional reality might be a holographic projection of information stored on a distant two-dimensional surface, fundamentally altering our conception of space and dimensionality. Quantum computing represents the most visible application of quantum principles to practical technology. By exploiting superposition, entanglement, and quantum interference, quantum computers can solve certain problems exponentially faster than any classical computer. The key insight is that quantum bits or qubits can exist in superpositions of both 0 and 1 states simultaneously, while a classical computer with n bits can represent one of 2 n possible states at any given time. A quantum computer with n qubits can represent all 2 n states. This exponential scaling allows quantum computers to explore vast solution spaces in parallel. Shor's algorithm, developed by mathematician Peter Shor, demonstrates quantum computing's potential by efficiently factoring large integers, a problem that would take classical computers longer than the age of the universe for sufficiently large numbers. This capability poses significant challenges to current cryptographic systems while simultaneously enabling new quantum cryptographic protocols that are provably secure. Other quantum algorithms show promise for optimization problems, database searches, and simulating quantum systems. Grover's algorithm can search unsorted databases quadratically faster than classical methods. Quantum approximate optimization algorithms tackle complex scheduling and logistics problems. Quantum machine learning algorithms might revolutionize artificial intelligence by efficiently processing high-dimensional data. However, building practical quantum computers faces enormous technical challenges. Quantum states are extremely fragile, easily disrupted by environmental interference. Current quantum computers require near absolute zero temperatures and sophisticated error correction protocols. Despite these challenges, rapid progress continues, with companies and research institutions achieving new milestones regularly. Quantum mechanics offers fundamentally new approaches to secure communication through quantum cryptography and quantum key distribution. These technologies exploit the no-cloning theorem, the impossibility of creating perfect copies of arbitrary quantum states, to detect eavesdropping attempts. In quantum key distribution protocols like BB84, two parties share quantum states to establish a secret key. Any attempt to intercept and measure these quantum states necessarily disturbs them, alerting the communicating parties to potential security breaches. This provides information theoretic security based on the laws of physics rather than computational assumptions. Quantum communication networks are beginning to emerge, connecting cities and countries through quantum encrypted channels. China's quantum communication satellite Misius has demonstrated intercontinental quantum key distribution, while terrestrial fiber optic networks provide quantum secure communications for government and financial institutions. Future quantum internet protocols envision connecting quantum computers across global networks, enabling distributed quantum computing, blind quantum computing for privacy-preserving calculations, and quantum sensor networks with unprecedented sensitivity and accuracy. Quantum sensors exploit quantum coherence and entanglement to achieve measurement precision beyond classical limits. Atomic clocks based on quantum transitions between atomic energy levels now serve as the foundation for GPS navigation systems and provide the time standards for international commerce and scientific research. Quantum magnetometers can detect magnetic fields billions of times weaker than Earth's magnetic field, enabling new medical imaging techniques and archaeological surveying methods. Quantum gravimeters measure tiny variations in gravitational acceleration, useful for geological exploration and monitoring groundwater resources. In medicine, quantum sensors might revolutionize diagnostic imaging and drug discovery. Quantum-enhanced MRI could provide detailed images of brain activity and tissue structure. Quantum sensing of biomolecules could enable early disease detection through ultra-sensitive analysis of biological samples. Quantum effects also play crucial roles in biological processes. Photosynthesis appears to utilize quantum coherence to efficiently transfer energy from light-harvesting complexes to reaction centers. Bird navigation might exploit quantum entanglement in specialized proteins to sense Earth's magnetic field. These discoveries suggest that life itself has evolved to harness quantum mechanical principles. The story begins in 1900, when Max Planck made a desperate attempt to solve a seemingly simple problem about how hot objects glow. His solution required assuming that energy comes in discrete packets, quanta, rather than flowing continuously like water from a tap. Planck himself didn't believe this radical idea, calling it an act of desperation. But he had unknowingly opened the door to the strangest realm in science. Within decades, this quantum revolution exploded across physics. We discovered that light behaves like both waves and particles simultaneously. We learned that electrons don't orbit atoms like planets around the sun, but exist in probability clouds of potential location. Most shocking of all, we found that measuring a quantum system fundamentally changes it, as if reality itself remains undecided until someone bothers to look. But perhaps no quantum phenomenon challenges our understanding of reality more profoundly than entanglement, a connection between particles so deep and mysterious that it troubled Einstein for the rest of his life. Unlike the other strange behaviors of quantum mechanics that seem to fade away in our everyday world, entanglement suggests something revolutionary about the nature of reality itself, that separateness might be an illusion, and the universe might be far more interconnected than we ever imagined. Before we dive into entanglement, we need to understand what makes the quantum world so fundamentally different from our everyday experience. Classical physics painted a picture of the universe as a collection of separate objects with definite properties, interacting through forces that travel at finite speeds. A baseball has a specific location and velocity. A light switch is either on or off. Cause precedes effect in an orderly chain of events. Quantum mechanics shattered this comfortable worldview. At the smallest scales, particles don't have definite properties until they're measured. They exist in superpositions, combinations of all possible states simultaneously. An electron can spin both clockwise and counterclockwise at the same time. A photon can be both vertically and horizontally polarized until someone checks. This isn't just a quirk of our measurement tools or a sign that we need better microscope. Multiple experiments have confirmed that quantum systems genuinely exist in these impossible-seeming combinations of states. The universe at its foundation operates more like a cosmic game of probability than a clockwork machine. Yet even this radical reimagining of reality pales compared to what happens when quantum particles become entangled. Here, the strangeness amplifies beyond individual particles to create connections that transcend our ordinary understanding of space and time. Quantum entanglement occurs when particles interact in such a way that they become part of a single quantum system, even after they're separated by vast distance. Think of it like this. Imagine you could create a pair of dice that, no matter how far apart you roll them, always show complementary numbers that add up to 7. When one shows a 6, the other immediately shows a 1. When one shows a 4, the other shows a 3. Every single time, instantly, regardless of whether they're in the same room or on opposite sides of the galaxy. But here's where the analogy breaks down, and quantum mechanics gets truly bizarre. These quantum dice don't have predetermined values hidden inside them. Before measurement, each particle exists in a superposition of all possible states. The moment you measure one particle and find it in a specific state, its entangled partner instantaneously knows what state it must be in to maintain their correlation, even though no signal or information travels between them. Creating entangled particles typically involves starting with a quantum system in a well-defined state, and then splitting it apart while preserving the overall quantum coherence. One common method involves passing laser light through special crystals that occasionally split a single high-energy photon into 2 lower-energy photons. These daughter photons inherit correlated properties from their parent. They're born entangled. Another approach uses atoms with multiple electrons. By exciting these atoms with precisely tuned laser pulses, scientists can create situations where 2 electrons become entangled in their spin state. When one electron is found spinning up, its partner will always be found spinning down, maintaining perfect anti-correlation no matter how far they travel. Albert Einstein, along with colleagues Boris Podolsky and Nathan Rosen, published a famous paper in 1935 that challenged the completeness of quantum mechanics. The EPR paradox, as it became known, pointed to entanglement as evidence that quantum theory must be missing something fundamental about reality. Einstein's reasoning was elegant and seemingly airtight. If quantum mechanics were complete, then entangled particles would need to instantly influence each other across arbitrary distances. But Einstein's own theory of relativity prohibits anything, matter, energy, or information from traveling faster than light. Therefore, Einstein argued, the particles must carry hidden variables, predetermined properties that account for their correlations without requiring instantaneous communication. This hidden variable theory suggested that quantum mechanics, while remarkably successful at predicting experimental results, provided only an incomplete description of reality. Somewhere beneath the probabilistic quantum formalism lay a deeper deterministic theory, where particles had definite properties all along, much like coins that are already heads or tails before we look at them, even if we can't see which until we flip them. Einstein spent decades searching for this deeper theory, convinced that God does not play dice with the universe. He believed that once physicists discovered these hidden variables, the strange probabilistic nature of quantum mechanics would dissolve into a more sensible classical picture of reality. But Einstein was wrong in the most beautiful and profound way possible. The universe really is as strange as quantum mechanics suggests. In 1964, Physicist John Stuart Bell published what might be the most important theorem in modern physics. Bell's work showed that if hidden variables existed, they would lead to specific statistical predictions about the results of measurements on entangled particles. More importantly, these predictions differed from those of quantum mechanics in ways that could be tested experimentally. Bell's insight was to consider measurements made at different angles on entangled particles. Hidden variable theories predicted that the correlations between these measurements should satisfy certain mathematical inequalities, now known as Bell inequalities. Quantum mechanics, however, predicted correlations that could violate these inequalities. Under specific conditions, the stage was set for one of the most important experiments in the history of science. If Bell's inequalities were satisfied, Einstein would be vindicated, and quantum mechanics would need modification to include hidden variables. If the inequalities were violated, then either hidden variables don't exist, or we need to abandon the idea that effects can't precede their causes, locality itself. Starting in the 1970s, a series of increasingly sophisticated experiments tested Bell's inequality. Elaine Aspect's groundbreaking experiments in France, followed by many others around the world, consistently found violations of Bell's inequalities that matched quantum mechanical predictions with extraordinary precision. These results didn't just confirm quantum mechanics, they revealed something profound about the nature of reality itself. The universe doesn't consist of separate objects with independent property. Instead, quantum entanglement creates genuine connections between distant parts of reality that transcend our ordinary understanding of space and time. The violation of Bell's inequalities forces us to abandon at least one of our fundamental assumptions about reality. Either realism is false, meaning particles don't have definite properties independent of measurement, or locality is false, meaning distant events can instantaneously influence each other. Most physicists accept that quantum mechanics violates locality through entanglement. When you measure one particle of an entangled pair, you instantaneously determine the state of its partner, regardless of the distance between them. This happens faster than light could travel from one particle to the other, violating Einstein's prohibition on faster-than-light signaling. However, this spooky action at a distance doesn't allow for faster-than-light communication in the conventional sense. While measuring one entangled particle instantly affects its partner, you can't use this connection to send messages. The results of quantum measurements appear random to any single observer. Only when both parties compare their measurement results do the correlations become apparent. Think of it like this. Imagine you and a friend each have a coin that, when flipped, always shows the opposite of what the other shows. If you flip your coin and get heads, your friend's coin will show tails, even if they're on mark. But neither of you can control what result you get. The outcomes appear random to each individual. Only when you communicate your results through conventional means do you discover the perfect correlation. This quantum non-locality suggests that entangled particles remain part of a single, unified quantum system, regardless of their spatial separation. Einstein's vision of the universe as a collection of separate, independent objects breaks down at the quantum level, replaced by a more holistic picture where distant parts of reality can share immediate, intimate connection. Understanding how to create and manipulate entangled states requires delving deeper into the mathematical structure of quantum mechanics. In the quantum world, the state of a system is described by a wave function, a mathematical object that encodes all possible measurement outcomes and their probabilities. For two separate particles, we might describe their combined state as a simple product of their individual states. If particle A is in state up and particle B is in state down, their combined state is simply A up, B down. But entangled states can't be factorized this way. Instead, they exist as combinations, superpositions of multiple product states simultaneously. A maximally entangled state might be described as A up, B down, plus A down, B up, simultaneously. This means the particles don't individually have definite spin direction. Instead, they exist in a combination where they're perfectly anti-correlated, without either particle having a definite state on its own. One of the most common ways to create entanglement involves parametric down conversion, where a single high-energy photon splits into two lower-energy photons inside a nonlinear crystal. Conservation laws ensure that the daughter photons have correlated properties. If one has vertical polarization, the other must have horizontal polarization to preserve the total angular momentum. Scientists can also create entanglement through carefully designed interactions between atoms, ions, or superconducting circuits. In these systems, quantum gates, analogous to logic gates in classical computers, can manipulate and entangle quantum states with remarkable precision. By applying sequences of these operations, researchers can create entangled states involving dozens or even hundreds of particles. The act of measurement plays a special role in quantum entanglement. Before measurement, entangled particles exist in superpositions of correlated states. The measurement process forces the entire entangled system to collapse into one of its possible configurations, with the probability of each outcome determined by the quantum wave function. This collapse happens instantaneously across the entire entangled system, regardless of the spatial separation between particles. When you measure the spin of one entangled electron and find it pointing up, its partner's wave function immediately collapses to the down state, even if it's light years away. Different measurement choices reveal different aspects of entanglement. If you measure both particles in the same direction, say both along the vertical axis, you'll find perfect anti-correlation. One up, one down, every single time. But if you measure at different angles, the correlations become more subtle and depend on the relative angle between the measurement directions. These angular correlations are what allow tests of Bell's inequality. By carefully choosing measurement angles and comparing statistics across many trials, experimenters can distinguish between quantum mechanical predictions and those of local hidden variable theories. The measurement process also destroys entanglement. Once you measure one particle of an entangled pair, their connection is broken. The particles no longer share the mysterious instantaneous correlation that characterized their entangled state. This fragility of quantum coherence poses one of the biggest challenges in developing practical quantum technologies. Entanglement is extraordinarily fragile. Any interaction with the surrounding environment can destroy the delicate quantum correlations that make entanglement possible. This process, called decoherence, occurs when quantum systems become entangled with their environment rather than remaining isolated. Imagine trying to maintain the perfect synchronization of two dancers while they're being jostled by crowds of people. Each collision disrupts their coordination until they're no longer moving in harmony. Similarly, entangled particles lose their correlation when they interact with stray photons, air molecules, magnetic fields, or any other environmental influences. The timescales for decoherence can be devastatingly short. In warm, noisy environments like room temperature air, quantum coherence typically lasts only microseconds or nanoseconds. This is why quantum experiments often require extreme conditions, ultra-high vacuum, temperatures near absolute zero, and sophisticated shielding from electromagnetic interference. Different types of entanglement show varying degrees of fragility. Some entangled states are more robust against certain kinds of environmental noise, while others collapse at the slightest disturbance. Understanding and combating decoherence represents one of the central challenges in quantum science and technology. Scientists have developed various strategies to protect entangled states from decoherence. Error correction protocols can detect and fix certain types of quantum errors before they destroy entanglement completely. Dynamical decoupling techniques use carefully timed control pulses to cancel out unwanted environmental interactions. Decoherence-free subspaces exploit symmetries to create states that are naturally protected against specific types of noise. Quantum entanglement lies at the heart of quantum computing's revolutionary potential. While classical computers process information using bits that are either 0 or 1, Quantum computers use quantum bits or qubits that can exist in superpositions of both states simultaneously. But the real power emerges when multiple qubits become entangled. A classical computer with n bits can represent one of two n possible configurations at any given time, but n entangled qubits can represent all two n configurations simultaneously in a single quantum superposition. This exponential scaling means that just 300 qubits could represent more states than there are atoms in the observable universe. Quantum algorithms exploit this vast computational space through carefully choreographed sequences of quantum operation. The algorithm manipulates the entangled qubits so that wrong answers interfere destructively, while correct answers interfere constructively, dramatically increasing the probability of measuring the right result. Peter Shor's famous algorithm demonstrates this power by efficiently factoring large integers, a problem that would take classical computers longer than the age of the universe for sufficiently large numbers. Shor's algorithm uses quantum entanglement to explore all possible factors simultaneously, then uses quantum interference to amplify the correct answer. Grover's algorithm provides another striking example, searching unsorted databases quadratically faster than any classical method. While a classical computer must check entries one by one, Grover's algorithm uses entanglement and interference to locate the target item with far fewer operations. Current quantum computers remain limited by decoherence and imperfect control over quantum state. IBM, Google, and other companies have built quantum processors with dozens to hundreds of qubits, but maintaining entanglement across all these qubits simultaneously remains challenging. Nevertheless, rapid progress continues with new milestones achieved regularly. Quantum entanglement enables fundamentally new approaches to secure communication through quantum cryptography and quantum key distribution. These protocols exploit unique properties of quantum mechanics to detect eavesdropping attempts and establish provably secure communication channels. The BB84 protocol, developed by Charles Bennett and Jelly Brassard, uses the quantum no-cloning theorem to detect interception. This theorem states that arbitrary quantum states cannot be perfectly copied, meaning any attempt to eavesdrop on quantum signals necessarily disturbs them. In BB84, Alice sends Bob a stream of photons polarized at random angles. Bob measures these photons using randomly chosen polarization filters. After transmission, Alice and Bob compare their measurement choices over a public channel, keeping only the results where they used compatible measurement bases. Any eavesdropper would have introduced detectable errors in this process. Entanglement-based protocols like E91, developed by Arthur Eckert, provide even stronger security guarantees. These protocols use pairs of entangled particles shared between Alice and Bob. The violation of Bell's inequalities in their measurement results proves that no eavesdropper could have intercepted and replaced the particles without detection. Quantum communication networks are beginning to emerge worldwide. China's quantum communication satellite Messius has demonstrated intercontinental quantum key distribution between China and Austria. European researchers have built quantum networks connecting major cities through fiber optic cable. Banks and government agencies are implementing quantum-secured communication systems for their most sensitive information. The future quantum internet envisions a global network of quantum-connected devices. This network would enable distributed quantum computing, where quantum processors at different locations work together on complex problems. It could also provide blind quantum computing services, where users could perform calculations on remote quantum computers without revealing what they're computing. Entanglement enables quantum sensors that surpass the precision limits of classical measurement devices. These quantum-enhanced sensors exploit entangled states to achieve sensitivities that would be impossible with classical technologies. Atomic clocks represent one of the most successful applications of quantum sensing. These devices use quantum transitions between atomic energy levels as ultra-stable frequency references. Modern atomic clocks are so precise that they would lose less than 1 second over the age of the universe. GPS navigation systems depend on these quantum clocks to provide accurate positioning information. Quantum-enhanced atomic clocks using entangled atoms can achieve even greater precision by reducing quantum noise below the standard quantum limit. These clocks could enable tests of fundamental physics, such as detecting gravitational waves through their effect on the flow of time, or searching for dark matter through tiny variations in fundamental constants. Quantum magnetometers exploit the quantum properties of atomic spins to detect magnetic fields billions of times weaker than Earth's magnetic field. Medical applications include magnetoencephalography, which maps brain activity by detecting the tiny magnetic fields produced by neural currents. Quantum magnetometers could also revolutionize archaeological surveys by detecting buried artifacts through their magnetic signatures. Gravitational wave detectors like LIGO use quantum techniques to measure incredibly small distortions in space-time. Future detectors will exploit quantum entanglement between laser beams to achieve sensitivities beyond classical limits, potentially detecting gravitational waves from the Big Bang itself. Recent discoveries suggest that biological systems might exploit quantum entanglement and coherence for essential life processes. While the warm, noisy environment of living cells would seem to destroy quantum effects instantly, nature appears to have evolved sophisticated mechanisms to protect and utilize quantum phenomena. Photosynthesis provides the most compelling example. Plants and bacteria convert sunlight into chemical energy with remarkable efficiency, nearly 100% in some cases. Recent experiments suggest that this efficiency depends on quantum coherence in the light harvesting complexes that capture photons and funnel their energy to reaction centers. During photosynthesis, energy from absorbed photons must navigate through a complex network of chlorophyll molecules to reach the reaction center where it drives chemical reactions. Classical physics suggests this energy would take a random walk, with much of it lost as heat. But quantum coherence allows the energy to explore all possible paths simultaneously, finding the most efficient route through quantum interference. Experimental evidence for quantum coherence in photosynthesis comes from ultra-fast laser spectroscopy studies that can track energy flow on femtosecond timescale. These experiments reveal quantum beating oscillations that indicate the presence of quantum superposition states in biological systems at room temperature. Bird navigation presents another intriguing example. Many bird species can navigate using Earth's magnetic field with extraordinary precision. Some theories propose that this magnetic sensing relies on quantum entanglement in specialized proteins called cryptochromes found in bird retina. According to this theory, light excites electron pairs in cryptochromes, creating entangled radical pairs with opposite spins. Earth's magnetic field influences these entangled spins differently, depending on their orientation, potentially creating a visual magnetic compass that birds use for navigation. While the evidence for quantum effects in biology remains hotly debated, these discoveries suggest that life might be far more quantum than we ever imagined. If biological systems can maintain quantum coherence in warm, noisy environments, they could inspire new approaches to quantum technology that don't require extreme cooling and isolation. Quantum entanglement forces us to confront fundamental questions about the nature of reality that go far beyond physics textbooks. If particles can remain connected across arbitrary distances, what does this tell us about the structure of space and time? If measurement outcomes are truly random yet perfectly correlated between entangled particles, what happens to our notions of causality and determinism? The phenomenon of entanglement suggests that the classical worldview of separate, independent objects may be fundamentally flawed. Instead of a universe composed of distinct entities that occasionally interact, quantum mechanics reveals a reality where separation itself might be an emergent property of our macroscopic perspective. Consider two particles created in an entangled state and then separated by millions of light years. From our everyday perspective, these particles occupy completely different regions of space and couldn't possibly influence each other. But quantum mechanics tells us they remain part of a single, indivisible quantum system. The distance between them becomes irrelevant to their quantum mechanical description. This holistic view of reality resonates with ancient philosophical traditions while challenging Western thought's emphasis on reductionism and separability. If entanglement is fundamental to nature, then the whole truly might be greater than the sum of its parts, not just metaphorically but as a basic feature of physical reality. Entanglement amplifies one of quantum mechanics' most puzzling aspects, the measurement problem. In the standard interpretation, quantum systems exist in superpositions until measured, at which point their wave functions collapse into definite states. But what exactly constitutes a measurement, and why does measurement seem to play such a special role in quantum mechanics? When dealing with individual particles, we might imagine that measurement devices force quantum systems to choose definite outcomes. But entanglement creates situations where measuring one particle instantly affects its distant partner. This raises profound questions about the nature of measurement and its relationship to consciousness and observation. Some interpretations of quantum mechanics assign consciousness a fundamental role in wave function collapse. According to these views, quantum superpositions persist until observed by conscious entities, making consciousness itself a basic feature of physical reality, rather than an emergent property of complex matter arrangement. Other interpretations avoid invoking consciousness by proposing that any interaction capable of recording information causes wave function collapse. In this view, measurement devices, environmental molecules, or even cosmic microwave background photons can trigger decoherence without requiring conscious observation. The many worlds interpretation offers perhaps the most radical solution, suggesting that wave functions never collapse at all. Instead, each measurement outcome occurs in a separate parallel universe. When you measure one particle of an entangled pair, the universe splits into branches where all possible measurement outcomes occur simultaneously. Our consciousness follows just one branch, creating the illusion of wave function collapse. Classical physics painted a deterministic picture where knowing the initial conditions of all particles would theoretically allow prediction of the entire future. This mechanical worldview seemed to leave little room for genuine free will. Our choices might feel free, but they would ultimately be the inevitable result of prior causes, stretching back to the beginning of time. Quantum mechanics introduces genuine randomness into the fundamental laws of physics. Measurement outcomes can't be predicted with certainty, even with perfect knowledge of the quantum state. This quantum indeterminacy might seem to provide the opening that free will requires, but random events are hardly the same as free choices. Entanglement adds another layer of complexity to these questions. If our brains exploit quantum processes, as some theories of consciousness suggest, then our thoughts and decisions might be influenced by quantum correlations with distant parts of the universe. This could mean that human consciousness participates in the same non-local connections that link entangled particles. Such ideas remain highly speculative, but they illustrate how quantum mechanics challenges our most basic assumptions about causality, locality, and the relationship between mind and matter. Whether or not consciousness directly involves quantum processes, the discovery of quantum entanglement reveals a universe far more interconnected and mysterious than classical physics ever imagined. Current quantum technologies primarily exploit entanglement between small numbers of particles, typically pairs or small groups, but the future lies in scaling up to create vast networks of entangled quantum systems spanning continents and eventually the solar system. The technical challenges are immense. Maintaining entanglement between even two particles requires extraordinary isolation from environmental disturbance. Scaling to networks of millions or billions of entangled particles will require revolutionary advances in quantum error correction, decoherence suppression, and quantum control techniques. Researchers are exploring various approaches to quantum network. Quantum repeaters could extend the range of entanglement distribution by creating chains of entangled particles that relay quantum information across vast distances. Quantum memories could store entangled states for extended periods, enabling more sophisticated quantum communication protocols. Satellite-based quantum networks offer another promising avenue. Space provides a naturally isolated environment, where quantum states can remain coherent over much longer distances than terrestrial fiber optic networks. Multiple countries are developing quantum satellite constellations that could eventually create a global quantum internet. Such networks would revolutionize not just communication, but computation itself. Distributed quantum computers could tackle problems too large for any single quantum processor. Climate modeling, drug discovery, financial optimization, and artificial intelligence could all benefit from access to vast quantum computational resources. As our understanding of entanglement deepens, researchers are discovering new varieties of quantum correlation that go beyond simple two-particle entanglement. Matter-tight entanglement involves complex correlations between three or more particles that can't be reduced to collections of pairwise entangled states. Some of these matter-tight entangled states exhibit even stranger properties than simple two-particle entanglement. GH-ed states, named after Greenberger, Horn, and Zeilinger, involve three particles in a superposition where they all share the same spin direction, either all up or all down simultaneously, without any individual particle having a definite spin. Cluster states represent another exotic form of matter-tight entanglement that could enable new types of quantum computation. In these states, particles are entangled in complex web-like patterns that allow quantum information to be processed through simple local measurements rather than complex quantum gate operation. Scientists are also investigating whether entanglement might exist in systems we wouldn't normally consider quantum mechanical. Some theories suggest that black holes might be connected through quantum wormholes, essentially entanglement-based connections through space-time itself. If true, this could revolutionize our understanding of gravity and the structure of the universe. Perhaps the most profound implication of quantum entanglement lies in its potential to unify our understanding of the fundamental forces and particles of nature. String theory and other approaches to quantum gravity propose that space-time itself emerges from quantum entanglement between more fundamental degrees of freedom. In this view, the familiar three-dimensional space and one-dimensional time that we experience aren't fundamental features of reality. Instead, they're emergent properties that arise from patterns of quantum entanglement in a deeper, more fundamental realm. Distance itself becomes a measure of how strongly different regions are entangled. Nearby regions share strong quantum correlations, while distant regions are only weakly correlated. Such ideas remain highly theoretical, but they suggest that entanglement might be the key to understanding how gravity relates to the other fundamental forces. If space-time emerges from entanglement, then gravitational phenomena, like black holes and cosmological expansion, might ultimately be consequences of quantum correlation patterns. These theories also raise intriguing possibilities about the nature of information and consciousness. If the universe fundamentally consists of quantum information processing through entanglement networks, then conscious minds might represent particularly complex information integration patterns within this cosmic quantum world. As we stand at the threshold of the quantum age, quantum entanglement emerges not just as an exotic physical phenomenon, but as a fundamental feature of reality that connects every part of the universe in ways we're only beginning to understand. From the intimate quantum dance between particles separated by cosmic distances to the potential quantum processes underlying consciousness itself, entanglement weaves through the fabric of existence at every level. The practical implications are staggering. Quantum computers exploiting entanglement will solve problems that would take classical computers longer than the age of the universe. Quantum communication networks will provide unbreakable security for our most sensitive quantum sensors will detect gravitational waves from the Big Bang and peer into the quantum world with unprecedented precision. But perhaps the deeper revolution lies in how entanglement changes our understanding of reality itself. The classical worldview of separate objects interacting through local forces gives way to a quantum reality where distant parts of the universe remain intimately connected. Separateness becomes an illusion of scale and perspective, while wholeness and interconnection emerge as fundamental features of existence. This quantum worldview resonates across disciplines and culture. Physicists find themselves rediscovering insights that mystics and philosophers have expressed for millennia, that reality is fundamentally interconnected, that observation plays a crucial role in determining outcomes, and that the universe might be more like a vast mind than a giant machine. As we continue exploring the implications of quantum entanglement, new mysteries emerge alongside new understanding. How does entanglement relate to the expansion of the universe and the nature of dark energy? Can quantum correlations explain the fine-tuning of physical constants that allows complex structures like stars, planets, and life to exist? Do quantum processes in the brain give rise to consciousness and free will? The answers to these questions will likely reshape not just physics, but our entire understanding of what it means to exist in this universe. We're discovering that we live in an entangled cosmos, where every particle carries information about every other particle, where measurement outcomes ripple instantaneously across space and time, and where the act of observation itself participates in the creation of reality. Einstein called entanglement spooky action at a distance, because it seemed to violate his intuitions about how the universe should work. But perhaps the spookiness lies not in quantum mechanics itself, but in how it reveals the true nature of reality, a cosmos where everything is connected to everything else in ways both subtle and profound. As we develop technologies that harness these quantum connections, we're not just building better computers or communication systems. We're learning to work with the deep structure of reality itself, partnering with the universe's inherent interconnectedness to solve problems, explore new frontiers, and perhaps even understand our own place in the cosmic web of quantum entanglement that connects all things. The quantum revolution continues, promising not just technological transformation, but a fundamental shift in how we understand ourselves and our relationship to the universe. In this entangled cosmos, we're not isolated observers looking in from the outside, but integral participants in an ongoing quantum conversation that spans from the smallest scales to the vastest reaches of space and time. The future beckons with possibilities we can barely imagine. Built on the solid foundation of one of the most beautiful and mysterious phenomena ever discovered, the spooky, impossible, and absolutely real connections that quantum entanglement creates between every part of our wonderfully quantum universe.